Before we can start talking about Newton's second law, we need to revisit the idea of mass. We mentioned mass earlier in the section on units, but now is a good time to look at it a little bit more deeply. So mass measures the amount of matter in an object, and there's a few important ideas about mass that's worth reviewing. First of all, its symbol is m, and its units are kilograms. Now, the mass of an object, because it's the amount of matter in the object, that mass is fixed unless that object is broken into pieces. And also, because it's a measure of the amount of matter in there, the object's mass does not change anywhere in the universe. Now, mass is not size, but it is connected to the size of an object by the concept of density, which is not something we will cover in this course. It's important to recognize that mass and weight are not the same thing. Students often get them confused because they are connected. And as you can see in this weight formula, the way they are connected is that weight, which is the force of gravity, is equal to the mass times g, which, if you remember, g is simply 9.8. So the weight is simply mass times 9.8, at least here on Earth. And so there's some key differences between mass and weight. Weight is a vector, whereas mass is a scalar, and in fact, mass will always be positive. Weight is a force and therefore is measured in newtons, whereas we said just a second ago that mass is measured in kilograms. And this is one of the key ideas that if you're ever trying to distinguish between two quantities in physics or science in general, if they have different units and those units have no conversion between them, then those two quantities cannot be the same. Finally, weight depends on the location, which means that your weight can change. Your weight on Mars is going to be different than, say, your weight on the Earth, but the mass is going to be the same, as we said, throughout the universe. So let's go ahead and talk about Newton's second law. And Newton's second law is the law that we're going to see over and over and over again in just a second. And the reason for it is that Newton's second law is essentially a formula. It says that F net is equal to ma. Here, F net is the vector sum of all the forces. And so what Newton's second law is going to do is it's going to connect our forces to acceleration. And why is acceleration so important? Well, in order to write down our kinematic equations and to predict the motion of an object, we need to know the acceleration in order to do so. So ultimately, this is going to be the key linking point between forces and kinematics involving acceleration. And that's why the second law will be our starting point for calculating an object's motion. This is what we're going to be using all the time when we're doing problems. And you'll see that in the next lecture. So let's just go ahead and look at some basic problems here before we get into some more advanced problems in the next lecture. In this case, what you have is a 2 kilogram object and it's got a force acting on it, okay? And before, what we were just given is the acceleration explicitly. And here we need to calculate it. And that's not so bad in part A. We simply write down Newton's second law, but this time in terms of A, and so A is F net over m. And so we plug in our values, simplify, and we get 15 meters per second squared. Now in part B, this is asking a question which is much more like the type of questions we've been seeing before. We want to know how far it traveled in 6 seconds. In this case, we're going to use the first kinematic equation, and now because we know A, we solved for it, we can now plug in our values, simplify, and get the distance, which in this case is 270 meters. Same thing if we want to know the velocity. This time we use our second kinematic equation, plug in values, and simplify to get 90 meters per second. And so I think you can see what we've really done is we've now written our problem in terms of forces, and now we have to go one more step to find our kinematic variables so that we can then predict and describe the motion. In this next problem, and this is maybe a little bit more realistic, what you have is an object that is initially traveling to the east at 4 meters per second. So when you watch, you can see that it's moving 4 meters per second when you first look at it. And it's experiencing two forces, one acting to the east and another acting to the west. And what we want to do is we want to find its position. And so this problem hasn't been broken up for us just yet, but I think it's pretty clear that if we want to find its position, we need to find its kinematic variables. And now, in order to find its kinematic variables, particularly acceleration, we're going to need to use Newton's second law. And so let's go ahead and do this. And so we'll start by drawing a picture, as we always do. In this case, just the box moving to the right. I'll go ahead and specify an origin in positive direction. The positive x direction is going to be to the right. And I don't need to specify a y direction because in this case, there is no motion in the y direction. I'll now start to write down my kinematic variables. I first write down the acceleration. And in this case, I'm just going to do a little bit of calculation in my head. Already, this problem is becoming a little more complicated, and you'll see in the next lecture that I'll enhance our problem-solving method to include a few extra steps to make this step a little bit more explicit. But for now, I think we can do. We realize that the net force in this case is negative 10 because the west force is 10 newtons stronger than the force to the east, and west is the negative direction. So in this case, our net force is negative 10, and our mass is 5 kilograms, and so we get an acceleration of negative 2 meters per second squared. Our initial velocity is positive 4 because it was moving to the east at 4 meters per second, and we chose our origin so that x naught equals 0. Now we can go ahead and start finding our position at 2 seconds, and we do that as we always do by first asking the right math question. In this case, what is x when t equals 2 seconds? To do this, we'll use the first kinematic equation, plug in our values, simplify, and arrive at 4 meters. And so we answer our question with a sentence. It is 4 meters to the east. In this case, to the east because it was positive 4. In part B, it's a similar question, so we'll just start by asking our question, what is x when t equals 8 seconds? We'll still use the first kinematic equation, plug in our values, and simplify to get negative 32 meters. And the answer to this question is it is 32 meters to the west because in this case it's a negative value, and a negative value signifies we're 32 meters west of our original position. So I think you can see how starting with information about forces and an initial velocity, we can ultimately use that to calculate the position, which is really the goal of physics, is to predict the motion of an object. And so now we just have one more step to tackle in our problems because we're only giving information about forces, and then we need to use that information about forces to calculate our kinematic variables so we can continue to solve. We'll look at some more advanced examples in the next section.